Welcome you all in lecture number 33 of Abstract Algebra MTL 6051. In this lecture, we are going to discuss what is the irreducible polynomial. Okay. Example of irreducible polynomial. And Einstein criteria of irreducibility. Okay. So let us first see what is irreducible polynomial. See the irreducible polynomial. If R be integral domain, what is R? R be integral domain. A non-zero non-unit is that non-zero non-unit polynomial fx in Rx is said to be irreducible if fx is product of two polynomials gx in Rx, hx in Rx, then either gx is unit or hx is unit. Okay, it means what is fx? Fx belong to Rx. What is the first condition? Fx does not equal to 0 and Fx is not unit. Fx is not unit. And second, if Fx is equal to gx into hx, then either gx is unit, either gx or hx is unit in Rx. Okay. If these two conditions satisfied by any polynomial fx in Rx, then this fx is irreducible over R. Okay, this is R. Now let us see the example. If fx is equal to 11 plus 33 x square, 11 and 33 from z, so this polynomial belong to zx. This polynomial is irreducible over q. Why? First see, fx is equal to 11 plus 33 x square. This is not 0 and 11 plus 33 x square is not 0 and fx is not unit. Fx is not unit. Okay, so fx is equal to 11 1 plus 3x square. Okay, this 11 we call it gx and 1 plus 3x square we call it hx. What is gx? Gx is unit. Gx is unit. Why? Since 11 inverse exists in QF. Okay, so gx is unit. So by definition of irreducible polynomial, fx, which is the product of gx and hx, is irreducible polynomial. Okay, similarly 4 plus 2x square, this fx 4 plus 2x square can be written as 2 plus x square. Okay, so this we call it gx into hx. What is gx? Gx is 2. What is hx? 2 plus x square. What is 2? 2 is invertible. So this is irreducible over q. But this 2 is not invertible in z. This 2 is not invertible in z. So this gx is not unit in z and hx is also not unit in z. Okay. So this polynomial is reducible polynomial in z. This is reducible in z. Okay. See, fx is equal to x square plus 1. Now, later on we will prove this example by EIC. Okay, EIC means Einstein irreducibility criteria. Irreducibility criterion. Okay, when we study EIC, after that, after studying EIC, we will see the fx is equal to x square plus 1 irreducible over. So see, fx is equal to x square plus 1. This can be factorized into x plus I, x minus I. This is gx and hx. Gx is x plus I does not belong to qx. Hx is x minus I does not belong to qx. Okay, so both gx and hx is not unit in qx. Okay, so it is irreducible over q. See, fx is equal to x cube plus 1. X plus 1, x square minus x plus 1, gx into hx. Okay, what is gx? Gx is x plus 1. And what is hx? This one is hx. Hx is x square minus x plus 1. Okay, but neither gx is unit, neither this is unit, nor hx is unit. Okay, if these two gx and hx are not unit, what is fx? Fx is not zero, not unit polynomial. It is product of gx and hx, and gx and hx both are not unit, so fx is not irreducible. Okay, now see, Einstein criteria of irreducibility. What is that? If fx is any polynomial of this form, okay, in zx, it means a0, a1, a2, an are integer. a0, a1, a2, an are integer. And if there exists a prime p, such that this p divides a0, p divides a1, this is a1, p divides a2, p divides a3, dot so on, p divides an minus 1, but p does not divide an. Okay, and p square does not divide a0, then fx is irreducible over q. What is fx? Fx is irreducible over q. Okay, see the example. Fx is equal to this. Now see, what is a0? A0 is equal to 2. What is a1? 6. What is a2? 0. What is a3? 4. What is a4? 6. What is a5? 1. Now, then consider p is equal to 2. This 2 divides a0, 2 divides a1, 2 divides a2, 2 divides a3, 2 divides a4, but 2 does not divide a5, and 2 square does not divide a0. Yes. Okay. So by EIC, Einstein criteria of irreducibility, this polynomial is irreducible over Q. See, x square plus 1 is irreducible over Z7. Okay. Later on we will see some more examples based on EIC. But let's see the different kind of example. X square plus 1. X square plus 1 is irreducible over Z7. See, if this polynomial is irreducible over Z7, then this polynomial doesn't have any root in Z7. Right? What it means? If fx doesn't have any root, what is fx? Fx is equal to x square plus 1. What is f of 0? 0 square plus 1, that is 1. F of 1. 1 is equal to 1 square plus 1, that is 2. F of 2 is equal to 2 square plus 2 plus 1, that is 5. F of 3. 3 is equal to 3 square plus 1, that is 10 modulo 7, that is 3. Okay. What is f of 4? 4 square plus 1, 17. 17 modulo 7, that is 3. Okay. Similarly, f5 is equal to 5, f6 is equal to 2. Okay. So all these elements are not 0. Means f0 does not equal to 0, f1 does not equal to 0, f2 does not equal to 0, f3 does not equal to 0, f4 does not equal to 0, f5 does not 0, f6 does not 0. It means x square plus 1 doesn't have any root in Z7. So it is not factorizable in Z7. So it is the irreducible polynomial over Z7. Okay. Similarly, consider this one. See whether this possesses any root in Z3. No? Then what is f of 0? F of 0 is equal to 1 plus 0 plus 0 plus 0, that is 1. What is f of 1? 1 plus 1 plus 1 plus 1, 4. 4 modulo 3 is equal to 1. What is f of 2? F of 2 is equal to 1 plus 2 plus 4 plus 8. That is 3, 7 and 8, 15. 15 modulo 3 is equal to 0. It means f2 is equal to 0. So this polynomial has one factor. This polynomial has one factor in Z3. It means this is reducible in Z3. This polynomial is reducible in Z3. Similarly, x square plus 1. What is f0? 1. f1, 2. f2, 5. This doesn't have any root in Z3. It means this is the irreducible polynomial in Z3. Okay.